In this video, I would like to point out some key features of bilinear quadrilateral elements and some more interesting facts and what more you can do with the particular quadrilateral elements. Now, the kind of quadrilateral element that we have already dealt with is a simple rectangle of this sort, and it has linear shape functions with 4 nodes describing the entire element. And we have 2 degrees of freedom at each node, so we have a total number of 8 degrees of freedom in the entire element. So there is a significant difference in the expected deformation behavior if you want to consider in-plane behavior or bending. Now, for example, if you want to use this kind of an element which is in-plane or flat to also describe bending behavior in a cantilever beam. Now, let's take as an example a short cantilever beam which sort of looks like this, and you have a load P, or like a traction on this edge which is acting in this direction upwards, and this is of course direction X, this is direction Y, and I want to represent this as an ideal Q4 or bilinear quadrilateral element which is rectangular right now. So I know here that it will have 4 nodes, therefore 4 degrees of freedom. Now, if I just consider any one element in between, like something around here, then I can make sort of a free body representation of it, which looks like this, which is again rectangular, and I have 4 degrees of freedom. What I actually expect to see in terms of bending behavior under this load P is that there is a moment which is acting on both the side edges here. So you have M1, which is acting on this element, and it should be able to deform somewhat in this manner. If it is, of course, if it is ideal situation. Yeah, not this one, really the yellow one which is inside. Okay, but what actually happens with the Q4 element is somewhat different. What you actually see is that there is this basic rectangular element, and it is flat because it can't move in that direction, and you see a behavior of something like this. So the equivalent moment that causes this deformation is different than the M1 that we expect it to be for bending. So with this condition for 4 nodes at the 4 different vertices, it's tending to basically stiff elements or a stiff reaction. This can be explained by actually calculating the relation between these 2 moments, M1 and M2, that is required to cause the actual bending in this beam or in the element. Now, the bending moment M2 is actually related to M1 by means of aspect ratio of the element. And if you have higher aspect ratio, it means that you require even higher moment to produce the same effect as M1. So that means what happens is your element is now therefore much stiffer. So I can write the relation for you, however, it's not very important this stage to really know how I got to it and why we need it, but it's more to see the difference. So the actual relation is given as this. A, B are the dimensions of the 2 edges, and you have M1 and M2. In an ideal situation, M1 is the one that shows bending, and M2 is the one that is for the current case of the Q4. So you see that it depends on the aspect ratio, and if the aspect ratio is high, then M2 also becomes higher. That means if we want to have any kind of element that actually doesn't show this overly stiff behavior, we have to use very, very small elements. And even then we will see some kind of stiffness, and that's called shear locking. So this is the phenomena of shear locking. Now, how do we solve this? It's okay that it exists, and we know that for these kind of elements under bending it will happen. So either we go for a very fine mesh, or we can avoid it by using a different element type. Okay, so the meshing strategy of course comes first, and then comes the type of element. We can also use internal degrees of freedom or extra degrees of freedom to get to a higher order element. So for example, we can, I would really like to write down at the end of this description as to what are the 2 different ways of improving this situation and what the phenomena is. So this phenomena is called shear locking, and to get rid of this you can either have a mesh strategy which is better, that means refined mesh, or you can have higher order elements. And you're aware of both the methods by now. So I'm going to move to the higher order element category, and I would say, okay, if I want to have a better relation, then I can have extra degrees of freedom in the system and go from a Q4 to a Q6. That means I am adding 2 internal degree of freedom in this system. Okay, and by introducing these 2 internal degrees of freedom, I can do this over here. So I can add another degree of freedom here, another degree of freedom here, and I will be able to see a much better deformation behavior. Okay, so this is an improved Q4 or an improved quadrilateral element with 2 degrees of freedom. So what happens is that I have 2 degrees of freedom which have a higher order. So it doesn't just depend on 1 plus R or 1 minus R, but it actually depends on 1 plus minus higher order. And that's how it makes it better. A better element, of course, is a quadratic element. This Q6 still has some limitations, and some of them, in some cases, it doesn't even exist. So the quadratic element is, quadratic quadrilateral element is better. So in this case, you have 16 degrees of freedom per system. That means you are adding additional nodes at every midsection of the edges. This is called a Q8. Now you can also have a variation of a quadratic element, which is a Q9. It's also called a serendipity element. You can see when you do the derivation why for the different shape functions, but you end up having 9 degrees of freedom, and the 9th one comes at the center of the element. The advantages of using such elements are no parasitic shear. That means you do not see any locking behavior, you do not see extra stiffness. You also need less mesh refinement, so that's of course good, and you get faster convergence, as with any good meshing strategy would give you as well. So these are some of the basic information about what the key features are, how you can improve it. So even in the case of triangular elements, you could have done the same thing by using higher order. You can do exactly the same thing also for rectangular or quadrilateral elements. Now I will not spend any time on the transformation matrices because they're exactly the same as they would be in the case of 2-dimensional elements like triangular elements. And in this case, you can use the direction cosines as angles directly for each edge because it's more uniform. So you can get the LM as the direction cosines, and it would be also applicable if you have a 3rd degree of freedom in the out of plane direction for bending. Of course, there you would have a 1 because you would not be changing anything in the transformation in that case. So it still remains the same. You can find some extra information in the lecture notes, but I will not spend any time in the videos on that.